Hey everyone, in this video we're going to talk about complexity analysis. So when we talk about complexity analysis, we're talking about two separate different things. So we have the time and we have the space aspect. So when we talk about time, we mean if an algorithm takes a long time to compute. So this time would be done by the CPU. Then if we go and talk about space, space would use up computer memory. So if we have an algorithm or we have a solution to a problem that has a high space complexity, it would be using a lot of additional memory. Now, this might be okay or it may not be okay depending on the situation. And then on the other hand, as far as time, if our solution or our algorithm takes up a large amount of time, it would take up a lot of CPU resources, and that may be okay or it may be not, depending on how big the data set that we're taking in is. So for example, if it was an array of less than 50 elements, it might be okay to have a time complexity of n squared. But if this was something that was taking in a data set of maybe tens of thousands of elements and it was likely to grow in the future, we might want to have more of a linear solution, or maybe possibly lower than that if possible. So let's just write down what we mentioned. So we said that complexity analysis is split into two separate parts. We have the space part and we said we have time. And we said that the resource that space takes up is our space in memory, so we just say memory, or we can also call this RAM, either or, they're both the same thing. Then when we go on to time, this is just our CPU power. So this is the real heart of our system, let that be a computer or a server. That's where all the work eventually ends up. So the next thing we want to talk about is why we use complexity analysis and not use something like speed. So for example, if I have a set of elements and let's say we have an array, and let's just put some numbers into our array. Let's say we have 2, we have 5, we have 8, we have 3, 1 and 9. Now let's say we've got these elements here in an array and we want to see how long it takes us to search for a given element. So let's say the element that we're going to be looking for is the number 3. So what we could do is, if we're going to take a linear approach, so this will be a basic solution to this problem, but we'd start off with our first element. We'd check to see if this is the number we're looking for, which is 3. If it's not the number, we'll continue on to the next element. So then we'd move on to 5, then we'd move on to 8, and then we'd move on to 3. And then when we find 3, we can say, yeah, we've got this element. This element is contained within this array, and we don't have to bother looking at these last 2 elements here. So that's the problem that we have. Now, if I was to create an algorithm to search for this given element, which is 3 in this case, my computer might do this in a very short period of time. It might be 300 milliseconds, let's say. So this is roughly 1/3 of a second. But maybe you are using a really super fast computer and you use the exact same algorithm. So we use the exact same code. It's in the exact same programming language, so there's nothing to interfere with there. It's exactly the same, but for some reason you end up being able to find the solution in 200 milliseconds. And this is nothing got to do with how good or bad the algorithm is. It's just the fact that your computer is much faster than my computer. And it's not really a good indication, because you could be developing algorithms and I could be developing algorithms, and we don't actually know whose code is more efficient, because both the systems aren't the same. And for us to get the same result, we would both have to run it on a system that was standard with their resources. So one way to get around this is not to measure by speed in terms of seconds or minutes or whatever. It's to use this complexity analysis. And the complexity analysis doesn't gauge how fast the algorithm is in a unit of measurement like seconds or minutes or hours, but it shows how the algorithm will grow. So if we go and look at a graph, when you look at graphs, some things can grow linear, some things can grow exponential, some things can grow logarithmic, and other things can be just constant. So I'm going to get rid of this and I'm going to draw out a graph and show you the different types of growth curves we have. So I've drawn out a quick graph here, and we can see on this axis we have our inputs. So our input will start at 0 and our inputs could go up to whatever our input is. So that could be maybe 10, it could be 15, or it could be 10,000 depending on our data set that we're dealing with. So we could always call this n, right? Because if we have 5 different inputs, in this case n would be 5. If we had 5 million inputs, n would be 5 million. And then on this axis we have time or space. And the reason why I'm putting time slash space is because we can do this for time or space. Both of these use the same type of graph, so it could be either or. Now, the first type of graph that you're probably familiar with would be something that looks like this. It's a straight line, right? And when we have a straight line graph, that means for every input that we get, our time or our space, so time again being the CPU power or space being the memory that it takes up, will grow in relation to that. So if we had one input and it took 100 milliseconds, if we had 5 inputs, it would take 500 milliseconds. Now, we use this term called big O, and big O is just the term that we use for complexity analysis, and we just represent it with an O, and then we have 2 brackets, and inside these brackets we have our type of growth. So in this example it's linear, so it'll grow as our inputs grow, so this will be big O of n. So again, if this was maybe 10 different inputs, we could say this would be big O of 10 for this particular example, but then we can generalize it by saying it's big O of n. So we can just fill in n with whatever number of inputs we use. So let's say we originally had 10 inputs and now we have 50. We could then represent n with either 10 or 50 depending on what input we have. Now, after our linear input, we also have constant. And constant is just basically a straight line to the time and space axis. And we can say this has a big O of 1. Or we might say that this is constant. So for example, no matter how many inputs we have, our time and space will not change. So the amount of memory or the amount of CPU power we need will always be constant, no matter how big or how small the input is. It's pretty difficult to get operations that are constant, but if you use the right data structure for inserting and deleting, you can get constant time, along with if you want to go and look up some data. So if you have a lookup table in a hash map, we can get that with constant time. So the lower we can get down on this graph, the better. So ideally we want to have everything constant time, but that's just not always possible. A good second alternative is logarithmic. So again, logarithmic would start off something like linear, and then it starts to branch off quite quickly, and then it doesn't grow that much more with the extra input. So we can notify this as big O of log and n. This is also really good for a complexity analysis point of view. Some of the more efficient searching and sorting algorithms can be performed in log of n under the right conditions, like quicksort for sorting and binary search for searching. So after this we have 2 more that we're going to go through, but these are not really ideal. And again, they start off quite similar and then they slowly start to branch off, and their input grows a lot more compared to the... And I've actually just realized that I mixed up my x and y axis. time and space should be on this axis while input should be on this axis. So if we go and look at this, this would be big O of n log n. And it's important to not get this confused with the previous one that we talked about, which was log n. So log n is much better than n log n. And then the last type of complexity analysis that I'm going to cover is exponential. And exponential again starts off quite similar, but then it grows in size very, very quickly. And we can notify this as being big O of n squared. And we usually want to keep away from any type of algorithms that are n squared. Now there is some other types like n factorial, but you don't really see it in solutions. It's also a very poor solution, so you want to stay away from that. Ideally, you want to be staying with something that's either linear or less, and most code solutions have the possibility of being able to perform a linear or better solution. If your solution is maybe n squared or n of log n, it might be worth thinking about what you can do to try and optimize your solution. And if you're curious what n factorial would look like, it's just a more extreme version of n squared. So again, it would start off quite similar, but then it would just grow really, really quickly. And we could say this has a big O of n factorial. But again, these are the main 5 ones that you're going to encounter. So if you liked the video, leave it a like, subscribe if you want to see more of this type of content, and have a good day.